Hi everyone, welcome to CS302. How's everybody doing today? Hope you all are doing good. I'm doing good, thank you, appreciate it. I think I'm back up to full energy per se. So last time we were talking about hashing, and so today we're going to just finish talking about hashing, and we should be done pretty much early, and then I guess we can do some Q&A in case anybody has questions in the tests. And then, yeah, well, that'll be the day because I will wait and defer to start graphing until next week. Or who knows? Maybe we'll introduce graphing. It depends. So, yeah. Assignment 12 is that the CSVO project? If so, I don't know. I mean, if you have questions, you can ask them. But other than that, I'm not sure what you want me to say about it. Uh, I think I have a video on it so you can see it in action. But I mean, it's just like a top 2D version of CS:GO, basically. So yeah. Uh, anyways, well, yeah. I mean, you should have gotten started on it at the beginning of the semester. But yes, if you haven't already started on it, you definitely should, so that you don't run out of time. You don't want to spend your Thanksgiving working on it. Then you better get going on it that pretty soon. But yeah. More importantly, though, is don't forget you have the test next class. So that is going to be running the same as before for the first test, which means that if you look under, I'm not gonna spam you reminders like I did for the first test. I think at this point you get it. But I'll tell you that the test is going to be available between, this is Las Vegas local time, Pacific time, between 1 and 6 p.m. So you can take it anytime around then. Okay? So yeah, I think that pretty much covers everybody's time period. So yeah. Uh, yeah, the point distribution is different. The exams still average to the same. It's just that the way the points are distributed on this one, it adds up to that. So it doesn't matter when you think about weights, all right? So you just think about the weights like, it's just the weighting system on this test is more traditional, whereas the first test like was uh was always made digital. So I just made it easy to do the math on. But ultimately, each test I think is worth what, 15% of the grade. So if you miss 340 points, that's 10% off. That would be the equivalent of you losing 10 points on the first test. So it doesn't matter what the point average is. Don't worry too much about that. I think the final is like 7 points. So that doesn't matter because it's still each half a point is worth like way more. So yeah. Ignore the point numbers. That's just it makes it easier to grade. In fact, it makes it easier to get partial credit because if a question's out of 200 points, we can give you like 180 points. We give you 170, 175. It's much nicer than giving you like 1.765 points. That's like not as nice to do math on. So that's why the bigger points allow for easier, more accurate partial credit. So, all right. Uh, Feel free to post any more questions about assignments and all those kind of things. Otherwise, I'll just keep talking about hashing. Like I said, we're like 20 minutes away from finishing hashing, so I'm not particularly worried about that. We'll have some spare time today. So, all right. So let's start by kind of giving a quick review about the two types of hashing that we sort of mentioned. First, of course, we have what a hash table is with a hash function. I think we don't need to review that. We kind of nailed that to the ground, but your hash function is what kind of tells you where to put things in your hash table. And so the hashing is good because it's fast. You're able to access things quickly and remove them quickly, uh, as long as you don't have collisions, right? And collisions, when you do have them, which again you don't want them, but when you do have them, from a storage perspective, there's ways to handle it. From a security perspective, is it's not good in general, so you never want them anyways. So you just don't have them. If you do, then you do a better job with the hash function. You just make it big enough that like it will be very unlikely. So anyways, you're trying to avoid collisions, but if you do have them, let's see how we deal with them. So we said, okay, we have two main ways of dealing with them. The idea being that, okay, we have a collision, we have to figure out where to put the data that collides, right? We can't just put things in the spot they belong because now we got to put multiple things. So we said, okay, we got to put multiple things. Let's make a list of them. All right, that's what separate chaining or close addressing is about. The concept of close is because we are still putting it in the same address that something was being hashed to. That's why it's called close addressing. The addressing doesn't change. Or the name that I prefer better is separate chaining because, I think of chain of linked list. So like that makes it easier for me to remember this is the one that has linked list in it. And basically what chaining is just basically making a list of either pointers like this of linked list or an ABL tree you could even make like that. Obviously the ABL tree is better because it's log n versus n with this. But neither of them are of course over one, right? And it turns out that like when you do a dictionary on Python, it's using separate chaining with ABLs. So that's if they use it, it must be the good thing to do, right? So that's pretty much all there's to it when it comes to separate chaining or close addressing. And the other option of doing is, okay, if you don't want to make a list of things in the same spot, then let's just kind of throw them somewhere else. And by that I'm saying, well, if I'm trying to hash a number right here, but it's already full, instead of making a list of numbers here, let's go and find somewhere else in the table that has available. And if we do find a spot, let's just dump it in there. And so that finding next spot available sort of explanation we're going to expand on that, on different ways to find that. The way that we kind of introduced last time is what was called as linear probing. And that was the concept of saying, okay, the 21, we're trying to put in, I think, what was it, 42 first, 8, 21, so 32. So when we're hitting 32, it should go where the 42 is, but there's already a 42. So with linear probing, what we're going to be doing is we're just going to look for the next available spot in a linear fashion. By linear, I'm saying you're going to add one every single time. Although in theory, you could be adding by increments of 2 and 3s and whatnot. So you have that flexibility. Linear probing is just the concept of kind of going one by one or by a fixed increment, which again is usually 1. So in this case, we said, okay, well, there's nothing on the index 3 because there was nothing with the 3 ending here. So let's just put in the 32 there. There's a lot of issues that come up with this though. Sure, we're able to like not waste space, which is one of the issues of separate chaining or just hashing in general is that, you know, you are usually going to have empty spaces along with the spaces that have valid data, right? That's the cost of hashing. And so with close addressing or separate chaining, there's no solution to that. Like if everything hashes to the same area, then you're going to have entire sections of your table empty. Close addressing is like, oh, okay, if you're really worried about space, then I actually can offer a solution to that. Because as you see, it just kind of looks to see like, oh, okay, well, this would have been the place to hash, but it's not there. So let's see what else is empty. Oh, well, the spot is empty. Let's just dump it in there. Let's say we threw in a 65 into this existing list. Well, that would try to go here, but because it's full, it would go here, right there. So open addressing, as the name implies, means that the addressing where something's going to end up is open-ended, so it can go kind of anywhere. The big downside to this is that if you try to access the numbers before, if I say, oh, well, is 65 there? Well, you go to the 5 because this is where it would hash to. And if you don't see it there, you can't just say, well, it's not there. Because you did open addressing, you have to look other places. And so you actually have to go linear probing. And until you hit an empty spot, you can't guarantee that like this thing is not somewhere else. So that is a big downside to this. So the only upside I would say to this system is that you are going to try to maximize your space, because with something like linear probing, as long as there's an empty space in this table, it'll find its way to fit there. For example, Let's say we were trying to insert 11 into this after what we have. Well, 11 would try to go where the 21 is, but that's already full. So you'd start the linear probing. So you go to the next one. It's also full, 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 full. And finally, assuming we don't have the 65 I said earlier, finally we see an empty spot here. So this probing method will find a spot. But now if we're looking for 11, we hash it. It says it should be here and it's not there. We can't just give up and say, well, it's not in our list. We know it's not because we see it, but also we need to figure out algorithmically how we can verify that. Well, there's no other way other than basically going around and saying, okay, keep checking through until you find 11. You're like, well, I guess it is there after all. Okay. Uh, Now we have a question. What if there are not spots in the table? So that's a limitation to this, right? So with any kind of hashing, you need to have space available, like, or think of like a queue, right? If that ends up happening, then yes, you just say, well, we're gonna need a bigger table, and you make the table bigger. But it's not as easy as just copy pasting the data. So that's what I was going to talk about when I get to load factor. But when you resize your table, it's not a matter of just like making a bigger table and copying and pasting everything in the same index. Because remember, the hash function that you made here, which in this one is just h of x is x mod 10, this hash function is assigned for a table of this size 10. If you make a table of size, let's say 20, your hash function, I mean, if you leave it like that, with linear probing, it's going to start filling up the first 10 spots, and once it finishes those, then the probing is going to start like filling the rest. But that's really, really bad. That's like horrifying. What you really need to do when you always resize a table is you need to modify your hash function to take advantage of that. Now that might be as simple as changing that final modulus. So most hash functions, the last thing you'll do is some modulus on the table size. Here, that's literally all you do. But like, you know, nothing stops you from running a hash function like this. Like that. And this is just basically saying if I throw in 5, it's going to multiply times 2. It's going to add 5 to it. It's going to get 15 out of that and then do mod 20, right? Nothing stops me from doing this hash function, but it's important that I have this at the end because that's the size of the table. That guarantees that we never get a value that doesn't fit in the table. Now this is strictly again for storing and for stuff, not password related. But yeah, so you have to modify that when you make a bigger table. Okay, so just be aware of that. And then after you modify the hash function, you have to reinsert everything. So you got to take all the stuff out from the old hash function, feed it into the new hash function, compute the new hash value, and then store it there. And hopefully, this is a good function that's going to distribute things, right? Because like you may have designed this function to be super good for like this range of numbers, but if all of a sudden now your table is like 100, it's not enough to just change this to 100 because like it's still probably not going to be optimized for that. So it's no easy task resizing your table because of that hash function update. Okay, uh, but we'll talk about more about when I say load factor, when the time should be to resize a table, because it's usually not. You don't want to wait until your table is completely full to resize usually, because think about it. Like this is from like a mathematical perspective, right? Like what are the odds that if I give you a dice or something, forget a dice. Let's say I just tell you to pick a number between 1 and 10, okay? And you pick a number. You say, oh, I pick 5, all right? So now I tell somebody else to pick a number between 1 and 10. But if they pick a number that somebody before them already picked, then there's going to be a collision, right? So now, whereas you had like 0 chance of a collision, they now have potentially a 10% chance of a collision, right? Okay, you keep going, and after like you fill in half the table, if you ask somebody else to pick a random number between 1 and 10, and half the numbers are now no good anymore, then you got a 50-50 chance. Those are pretty high odds, actually. So the higher, even if you have a really good hash function, the higher the table is full, the more likely that you are going to have a collision. One of the things that I make people do on tests and on like when you're coding this. In fact, on the worksheet that you have up there for the hashing. Actually, you know what? When is that worksheet due? I want to make sure it's not due too late. But even if it's due after the test, you want to make sure you do it before the test because that's just, remember the past test? You saw those questions were the same. The worksheet for hashing is literally going to be your study guide. Yeah, so the worksheet for hashing is due on November 13th. So I'm not going to move the date up because that'd be kind of cruel at this point. But it is available starting right now. So definitely spend the next 2 days looking at this, and if you can, finish it and use it as your study guide. Okay? So it's already available now, and it does have some questions on hashing that you want to do because they're going to be exactly the questions you're going to get on the test. Like I guarantee you. Okay? So yes, it is due on Saturday, but I would recommend you do it before the test because it's a study guide. I just don't want you to get bogged down if you can't answer something with it. You can worry about it later. But like this question right here, you're gonna get an identical question to the test, like guaranteed. Not the same numbers, but the same question basically. And so you want to be able to do this. All right. And also the other questions about trees, which you can already answer if you study for the test already. And it can be a good thing for to test yourself. Now that fingers crossed, you've actually been reviewing for the test. Uh, if you try to do this right now and you ace it, then you know you're ready for the test. But if you don't ace it, then you know what you need to focus on. Okay? You got things like trees and APLs and building the tree from traversals and all that good stuff. Okay? So yeah, make sure you take a look at that, and I would encourage you to do it before the test due date. Okay? Um, and of course, ask questions as you do it. Okay, so as I'm saying, resizing not easy, but anyways, going back to this, here comes an issue. All right, suppose that I just inserted the 11, and now I'm going to go ahead and remove something. I'm going to go ahead and remove the 55. So I, hash 55 to this. I get a 5. I see that there is 55. I remove it. Suppose now that I say, is there going to be a 11 in this list right now? Well, 11 should be found in spot 1, which of course is full, so that means that it could have been put somewhere else. So I'd start scanning, and then I see an empty spot. So I might say, incorrectly, but I might say, oh, well, if an 11 would have been inserted here, like if an 11 was present in this list, it would have gone there because that spot is empty, And it is true, if I inserted like something ending in like 1, so like an 81, this is literally where it would go because it's the next available spot. So I can make that deduction that, well, because it's empty, that means that there must not be an 11 because otherwise it would have been there. And so I say 11 is not found. Of course, we know that's not true because we can see it. The 11 is here. So the reason I'm saying this is because when you're trying to identify if a number is present in the list, it's not enough to just look for the number and then give up when you see an empty spot because you could run up into this exact situation. Okay, so what do you do then? Do you just have to look through the entire array? Well, not quite. There's a little trick that you can do to at least somewhat alleviate this. So I'm just going to copy and paste this though into duplicate. That way I don't modify the version that I had before, just in case we need it later. But yeah. So here's something that we can do to avoid that issue that I just brought up. So suppose we have the current numbers here. We have we have the 55, we have the 11, and let's just say we're going to insert a 81. Okay, so the 81 does go here. Very cool. Now let's say we want to remove the 55. Okay, when you remove something from the list, don't just delete it. Mark, which means add a Boolean array as part of this. or if it's an object, then just add one more field. And then mark this as was, it had something but was deleted, versus like this, which has never had anything in it. Okay? If you add that extra piece of information, oops, drop the pencil a second. If you add that extra piece of information, then you don't run into this problem, because let's say you're looking for 11 now. As you hit these numbers, you see that they have valid data, so you just keep going. But when you hit the 5, index 5, you see that it's empty, but you have the boolean that says, yes, it's empty, but something was here in the past. And because you know that something was there in the past, that means that that something was deleted, but it was there, which means that if it was there in the past when you inserted a potential 11, you would have had to skip the spot and go on to like the next spot or way down the list. So by knowing that there's a piece of information, you know not to stop checking, and you can keep going. And of course, you find the 11 and you're good to go. All right, suppose you're looking for the number 31. You start out at the 1, and then you keep doing your linear probing. Again, you hit the empty spot, but it's not truly empty. Like, well, it is empty now, but it hasn't always been like this. At some point, it was populated. So you know to keep going, and you keep going. Finally, you hit the 8, and then you hit the 9. And when you hit the 9, then you're like, okay, this spot is empty, but unlike the spot from 5, it has always been empty, because your Boolean says, this is true and this is false or something. Then you know that the item is truly not here, because it would have had to go in that spot. Okay? So as long as you add that extra Boolean piece of information to each of these entries, then you can work around that, and you don't have to check the entire list and make this O of n. It's still going to potentially be O of n, but it's like optimizing bubble sort. It's at least some form of optimization. Okay? One more thing I wanted to mention is what happens when you hit the bottom of this. Do the same logic that you did with the circular arrays. Sorry, circular queues. You just wrap around to the top and keep adding things. That way you always keep, maximize inserting things in there. Okay? So like if you insert a 99, you put it there, and then if you insert like 109, then from here, the next spot you go is 0, so you would put it here. Okay? So that's what I'm talking about. So, yep, that is something useful that you want to do on any kind of probing that you're using, this little boolean. Okay, so this is linear probing. Let's talk about from like an analysis, like algorithm analysis point of view. What are the downsides to this? I mean, well, there's a lot of downsides versus this and like separate chaining. But within linear probing, what is a downside of the system? And this is actually the same issue that affects separate chaining, and that is this idea of clustering. Suppose that you have a bunch of, well, all this stuff can be solved with a good hash function, but suppose you don't have such a good hash function. So we still got the same hash function as before. But like suppose that your data is something like this. Okay? And you're going to insert it, and your hash table is of course of size 10. We're going to need more lines here. There we go. Okay? So suppose that I say go ahead and insert this. So you go ahead and you feed it into the hash function, and it tells you put it on the 28, so the 8 there. Then you get the 21, so you get that. Then you get the 31, which of course gets a collision, and then uses probing and goes to 31. and then you get another collision. This time you got to do 2 comparisons to finally find an empty spot. And then for that, 3 comparisons as you go and see this. And then the 22, because of the ones, it's, that wouldn't have had a collision if it wasn't because of the other stuff for the ones. So the 22 actually ends up also getting unnecessary collisions and going all the way there. And the 22 in the same story goes all the way there. So it's pretty nasty. So notice something about this. This I know we did fill the table quite a bit, but you can see that like the table is very clustered, which means that like this section of the table is really full. And like suppose that like I actually used a bigger table and you know, well if I did mod 20 this thing might be different slightly. But yeah, let's go and say no, I don't want to do that because I have to redo the math. But appreciate that like you can see how all the numbers, because of what numbers I picked, are tending to go in the same area of the table, right? We have like a lot of, not a lot, but we have some empty spots here. In fact, if I got rid of this 28, which was the first thing that we got, you can see how like the whole bottom of the table slash beginning is empty, right? What I'm getting to is that this is a normal occurrence when you're doing things in like math and whatnot. Clustering is a normal thing that happens. You look at like a bell curve and whatnot. Things tend to bunch up together, and so linear probing does nothing to alleviate that. Neither does things like separate chaining. The only way that you can alleviate that is by doing a better hash function that has one of those properties that we talked about that like evenly distributes the data. It's deterministic, but it feels random where like a tiny change in the input makes a massive change in the output, which is the best way to avoid this kind of clustering with the hash function. But again, we can't make a better hash function and we're stuck in this situation. What can we do? Well, that's where your other kind of probing methods work. Let's talk about quadratic probing and how that's going to help to alleviate this problem. Quadratic probing is another probing system, but instead of going in a linear fashion where you're like checking one spot and then the next spot like beneath and so on, you are going to be using exponents for that. So instead of checking, say, if you're hashing to index 1, in linear probing, you're going to check index 1, 2, 3, 4, 5, and so on. With quadratic probing, there's 2 ways to do it, but you're basically going to double the number you check each time. So you're going to go 1, 2, so it's going to be the same as linear, but then you're going to go to 4, and then from 4, you're going to go to 8, and then you're going to go to 16, to 32, and so on. So this is going to be basically powers of 2. And of course, quadratic equation or parabola, things like that. You can see that it's a power. So why would you do this? Well, let's see what this physically looks like if we had a bigger hash table. Here's spots 1 right here, and spots 2. And we got 4. And then we got 5, 6, 7, 8. And then like way down here, it's probably going to be like 16. And then if we kept going, somewhere down here, it's going to be probably 32. Okay, if we did it somewhat to scale. Suppose that, we have the same sort of hashing that we had before. And we get that clustering happening right here. If you have something like this with linear probing, suppose I were trying to hash right there at 1. So like a flash of light. If that happens, with linear probing, you got to do like a bunch of checks here. Probably somewhere like 8 or 9 checks just to get to the next spot. And again, if we get into the 1, we got to do the same number of checks plus 1. With quadratic probing, we only got to do 1, 2, 3, and we're good to go. Or look at that, 4, and like we're really good to go, like way away from clustering. Okay? So quadratic probing gives you that ability to kind of jump away from the clustered data quicker and into the like non-bunch stuff. It's like you're trying to find somewhere nice to sit in like a big cafeteria, and instead of checking every single spot, right? That's not a good example. Parking lots. Instead of trying to find like the closest spot, you try to look for spots that are further away because it's less likely that like people will be there, right? Because people like to park close because they don't want to walk and exercise. So ultimately, or maybe they're just carrying very heavy stuff. To be fair, yeah. But yeah. So with quadratic probing, it's that idea of like, okay, if things are really like you know colliding often here because everything's bunched up, then let's just quicker look out into the outer regions where there's probably more space. Now, this does solve the clustering problem, but does introduce other issues. Suppose that like the clustering really ended right there, you know. Well, actually, let's say that it ended after the 8, so like there. With the with the collision stuff, yeah, sure, we avoid all those collisions, but we're also gonna end up like, let's say we start filling other things here, we end up wasting a lot of space though, all the space right here, right? So quadratic probing's disadvantage is that its advantage is that you're going to basically avoid, get out of this with less comparisons, get out of this cluster area quicker. Disadvantage is that it does use up more space because you don't always fill everything up because of the exponents. With linear probing, it's like you're really filling that parking spot and like parking lot. So like as long as there's a spot, it will be found and it will be full. Quadratic probing, it's like, okay, you see that the first couple of spots next to the enders are full, and you just slide out, go straight to the way to the back of the lot. So like you end up with two clusters now. You end up with a cluster at the front and all the way at the back of the lot, and the middle's all empty. It's kind of like that. A little bit of exaggeration, but it's kind of like that. That's the disadvantage of quadratic probing. It can solve your problem a little too well that it causes other problems. Now, it is mentioned in the chat. Someone's mentioned that quadratic probing could be things like 1, 4, 9, 6, and 25. That is another way of doing it. Uh, it depends on if you're doing it as a power, as an exponent. So, whereas like if you at the end of the day, these are all hash functions. In fact, think about what linear probing's hash function is. It's just going to be probably x and then plus 1, basically. Every single time that you feed it, you just plus 1 it, right? And if you do something like this, then yes, you would end up with something like that, where you get the 5 and everything just squared. So both ways will work fine, okay? But the basic idea is that you want to have that increment happen in a bigger jump each time scenario. You could do it with not quadratic, but like cubic or something. Those are bigger jumps even. Ultimately, we just kind of separate it and say there's linear and then there's bigger stuff. In fact, when we talk about the third method, which I will now, that is known as double hashing. And you could even say that linear probing and quadratic probing are a form of double hashing. What double hashing says is that if you feed it something to your hash function and you get a collision, instead of doing a linear probing, instead of doing quadratic probing, use some custom defined function that you're going to feed it to. And that custom defined function could put it somewhere completely different. You have that power to decide what you want that to be. It could be as simple as instead of doing, +1, you do +2 every time. It could be something using powers. It could be something using some fancy math. It could be just its own little formula, which again is like a second hash function you feed it to. Now you might say, oh, okay, well, you might get ideas like say, okay, well, I'll just make a really good second hash function and then you'll never have the issue of collisions. Well, if you really do find a solution for that, then you could literally just combine both hash functions and just like plus them together or something. And that's probably a better hash function in the first place, right? So double hashing may sound like a solution to all problems, but it's not. I think the solution to all problems is really just make a good hash function, which I have hand waved and told you that I'm not gonna tell you how to do that really well because it's very hard. But yeah, just be aware. You know, you want to make a good hash table, make a good hash function. Otherwise, patch it up with all this collision resolution stuff. So yeah, those are the three ways that you can do your collision resolution, and on the test you will basically do one of each. You'll come up with the one. I think I tell you can pick your own double hash function, so you can say +2 or whatever. and so on. Okay. It's important though that you indicate to me with like either lines or arrows how you're jumping and checking things. Finally, like I said, I was going to talk about load factor, so let's talk about that. So I'm going to bring this little table in. Again, we had like the natural, bell curve distribution here. Uh, as I was saying, when a table gets more full, even though you have a really good hash, like okay, you could have the best hash function in the world today, and there's still a chance of collisions. Okay, but if the table is empty, the odds of you actually picking the thing that's going to collide is very unlikely. If you got something that is like 80% full or 90% full, and you go ahead and you try to pick a new value, even though you have a really, really good hash function, you just have a really high odds of actually getting a collision. Because think about it, you have infinite inputs on a fixed size table. So of course it's going to be collisions. Unless you have a table of infinite size to match your infinite output, you're going to have, there's a possibility of a collision. And the more full it is, the more likely that collision is going to happen. And so we have this little quote unquote formula called load factor, which allows you to compute just how full a table is. And it's just as simple as saying, okay, well, how many items do we have in the list divided by how big the list is, right? So if you have 5 items and the list is a size 10, your load factor is 50%. Half of it is full, right? And so it's good to know that because you don't want that load factor to get too high. You play around with that, you find the value that you like, and probably I would say keep it under half, maybe even under 30% full. And then now we're talking into a more optimized table that is less likely to have a collision. Okay? So rather than waiting for a table to get full, you usually wait until the load factor gets past a certain threshold before you think about resizing and making a new hash function. Because again, this isn't like a queue where like you wait till it gets full and then you resize. If you want to keep things somewhat optimal, you want to resize way, way before the thing gets full. Okay. Um, One last thing I want to say about double hashing, by the way, just in case you see this in other places, we think of h of x as the first function. Usually you see g of x as the second function. And I can do some examples of double hashing if you'd like. Like I said, you have one on the worksheet. It's a matter of picking a function and like, if you got your table and you got 42 and you got mod 10 as your first hash function, you know, that's going to go under the 2, right? And then let's say that you have 52. You feed it, you have a collision because it also goes into 2. You look at what your g of x second hash function is. Maybe that's just like x plus 2, okay? Or x mod 10 plus 2. Or simply say h of x plus 2. That means that this should go under what? 2 plus 2, which is 4. So index 4, you put 52 there. Okay, so that's an example of that. All right. So like I said, that's all I have in terms of material. I can answer questions for review for the test. I can do more hashing examples if you'd like. I can answer questions on the final project if you want me to, since you mentioned that. Uh, if we really have nothing to talk about, then I'll do an introduction into graphs. But I'd rather review for the test and whatnot. But I don't want to just repeat stuff. I'd rather you all ask. What if GFX also causes a collision? That's a good question, actually. So with double hashing, you can do triple hashing, but that would be kind of nasty. So usually you just repeat the double hash. So like, let's say that we're going to insert 32 now. So if you feed 32 into this, you get 2, which there's a collision already. So you feed it into this, which 2 plus 2 is 4, which is already a collision. So you just feed it back into this. So you get 4 plus 2 again, which is 6. So then they would go there. So you just keep feeding it to the second hash function. So yeah, that's a good question though, because I should have mentioned that probably. So well on you for asking that. By the way, the twice assignment is out. The extra credit, I mean, so if you really bombed the last 2 extra credits, you have that chance. So yeah, just ask away if you have any questions. Otherwise, graphing time. Good question. So we did all the survey stuff. Good news, I guess. If you're keeping up with our project, we were able to submit the paper by the deadline of November 5th to the conference. We'll find out if we get accepted in a month or so. Now that we finally finished that part, which was the timing scary stuff, uh, I can worry about like this, giving you your points. So what I gotta do is like I gotta download the logs and the submissions and match everybody's, generate those lists of names, give them to the TAs, and then have the TAs give you the points. So it's probably gonna take like 2 weeks, probably not before Thanksgiving. So yeah, just be patient on that. I think we got over close to 100 submissions. I think anywhere from 70 to 100. So it's gonna take some time to do those because we don't write a program. Hey, extra credit. Write a program that can do the matching for me. No. Uh, we just have to sit down and like do the matching. It's a little painful, but it's great though because like a lot of people found a lot of issues that we can fix and we can test. So I'm very happy about it, but it'll take some time for you to get the points. So just be patient. Do you have a good source for recurrence for traverses and tree balancing? Well, those are different things. Uh, for tree balancing, there's a really cool website. Glad you brought that up. I have a link on Canvas, but like at this point, like Canvas, what I do is like I add stuff every semester, links that I find and whatnot, and then I re-import it for the next 302. That's how we got this like massive Canvas thing. I like it though because it looks like I spend a lot of time building the Canvas website. Like you go take some classes and like you go to Canvas and like there's like one link and that's it, and it's kind of like, oh, that's sad. Okay, or you just get information overload like this one. So it's somewhere in there. Uh, if I find it, it'll be a miracle. Let me see. ABL tree reference, maybe that one. It's a link to. It's like a web. Oh, did I really get it on the first go? Oh wow, I did. Okay, cool. Here, I'll post this on Discord. Oh, not Discord. Chat. If you go to this link, and I'll share my screen in a second to show you. It's very cool. It's great for practicing your assignments. Uh, because you can click on this and like you can see a bunch of things. It's not just for ABLs. They got all the data structures here, like even sorting, um, and all the graphs that we're gonna talk about. But here's the cool thing: you can insert things into this. Why is it cut off? There we go. And then like well, someone beat you to it, I guess. But here, like for example, insert 444. Like this is so lit. I just don't like to use this as teaching because it's not mine, so it doesn't feel right just taking their stuff and using it. But I'll definitely show it off for them. Like look at this, look at this. It's gonna do a rotation. Look at this. Like, damn. Um, so yeah, it's really fun. Like it's just fun doing this thing. Let's see if we can get a double rotation going. Can we do decimals so that I can? Oh, no, it just ignored the dot. Okay. It's fine, not to worry. Let's do 127. All right. See that? And like, if you're like, whoa, 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 what just went down? You got your replays here. I haven't used this in a while, but I know you can do this. You can pause it and then you can rewind it and then like do like slow mo. Yeah, yeah. So like slow it down and then play. So it's doing the comparisons and look at that. So you can see it in slow mo. So you can get a better idea of what the rotation's happening. So this is great for balancing stuff because I mean I'm assuming that's what you're talking about, how things happen. So yeah, check them out. This is from that university, San Francisco. Okay, that's what I thought it was, but yeah. So yeah, so pretty cool. As for recurrence relations, I think the book that I link as part of the course, the one that's free, there's like a PDF, like a legal PDF, has a bunch of examples on recurrences that you could look at. Outside of that, probably ask your math teacher, assuming he knows about that stuff, which I guess he doesn't really know about full versus complete trees, but maybe he does know about recurrences. So yeah, uh, good for review. Definitely good for review because you can. It's like test yourself. Try to put something in, and then and then see if the rotation is what you expected. Oh, yeah, I gotta speed up the animation now. So then it's gonna whoop. So yep, perfectly balanced. That's all things should be. Okay. Other questions? By the way, there's a Python script for graphs that is really cool. I've been using it, but I forgot the name of it. I'll look it up once I get back. Um, it's great for visualizing graphs. So no one has any questions? You all ready for the test then? If you have a DRC accommodation, make sure you send me an email by tonight. I sent out an email yesterday, but I only got one contact, so I want to make sure that I get everybody's who has the accommodation, so I can give you extended time or whatever the accommodation may be. Yep, no more emails since then. Well, I'll give you 3 more minutes of silence, and then I'll start graphs if nobody has any questions. Is exam 2 same format as exam 1? Yep, same format. Although there's more drawing, so be prepared for that because you have all the ABL trees and stuff. Like I said, check the worksheet that came out today, and those are going to be your questions that are going to be like there. So you know, make sure you're able to answer those kind of questions digitally. That'll be a good practice. So, will there be any graph algorithms you for the exam? Dijkstra's? No, that we haven't covered Dijkstra's yet. That's the third exam. The stuff for the second exam is from whatever we finish in the first to the third second. So pretty much all the tree stuff and hashing. I think I did put a bonus question on the test related to the crypto uh, hashing stuff that I talked about. So you'll see that question out of 0 points, but it's extra credit. Yeah, we haven't covered Dijkstra yet. Dijkstra will come in a couple of weeks. We got 1, 2, 3 weeks left of class. So we'll be doing Dijkstra, minimum spanning tree, breadth first search, depth first search, we have time, we'll do 2 minimum spanning tree algorithms, Kruskal and Prims. If not, we'll just pick one, probably Prims. And I'll go quickly over the other one, but like not in detail. And then next week we'll do DFS and BFS. Okay. All right. That was your 3 minutes. So let's do graphs then. All right. So you might think we're done with trees, but we're not. It's never over. Yes, you have class during study week, um, which is pretty early this time around. It's like literally November 29th to December 3rd. Um, I try to make the last day a review day, but we'll see. It depends on how quickly we go. I mean, we're doing graphs today, so we might actually have that review day time. Depends on how quickly we go. But yes. All right. So graphs, graphs. We've been talking about trees for the past month or so. Graphs are really just like trees are a subset of graphs. So we're just going to expand our views into things that don't have more than just two nodes, like left child and right child. So first, let's start by defining what is a graph. And for that, I have pretty pictures. So the question of the day is, what is a graph? Okay? Well, let me start by giving you the fancy definition of what a graph is, which is that a graph is going to be a collection of vertices and edges. And typically, at least for this class, unless math might be theoretical, or whatever, it's a finite set of these vertices and edges. Okay? So, what does a graph look like? And then I'll define what vertices and edges are. Okay? Well, for that, I already told you in a way that the trees we've been doing are actually graphs, but let's see what like a more natural graph looks like. The kind of thing you would see if you go in the wild, go to the forest, and run into a mathematician or something. I don't know. This is more of what you think about when you think about a graph. You got a bunch of little nodes or vertices, and they're connected, some of them, not all of them. And if they are, not always like all connected between each other, yeah, which has a term for that. But it's made up of that. You got a line, circles, that's pretty much it. So, what are these lines and circles called properly? Well, I try to color code this to make it easier. But the vertices are going to be the red ones, and the edges are going to be well, I think that's blue. So, the blue ones, okay? So, the edges are what connect a pair of vertices. Okay? So those edges are connecting your vertices, and that can mean a lot of things. Like it can mean a relationship. Like think about social media. Each edge might be a friend that you're connected with, like someone that you know, and you have their phone number or their Instagram or whatever that might be. And the vertices are, of course, each of the persons. It could also be mapping. So like think about like the app that we did, the AR navigation app, right? So each of those areas that you saw was actually a vertices, and the edges were connecting all of the arrows. And that's how we made the path between the start and the destination. And so those are your edges. We only want to put edges where there exists a path. So like let's say we have two vertices and there's a wall between them. We don't want to connect those two with a line or an edge because there's no way to get there because there's literally a wall. Now I know some of you ran into walls when you were running the project. That was a bug that we had where it flipped the coordinate system or it thought it was in the wrong room. But in theory, you wouldn't kind of run into walls and whatnot. So that's what a graph is. So we got a collection of these vertices and edges. So let me actually write that. So we got a collection of these vertices and edges. They're finite for our usages. And so that we understand those vertices, or as I will usually call them, nodes, because of the tree stuff, uh, are the data, and then the connections are the edges, and it's usually between a pair. You don't have like three things like connected. Because I mean, yes, you could have things connected in series and whatnot, but those are separate edges from each other. How you actually write those is like this. So you want to define the list of edges and the list of vertices of a graph. That's because you want to give them a name and you want to see how many there are. So here you can see that I write V for vertices, and then I list them in curly braces. So they all have an identifier. I think of it like variable names, right? So we got all these A, B, C, D, E, X, and Y. I just list them and I comma separate them. When you're writing this mathematically, the order doesn't matter. I could have written this as like X, comma Y, B, A, and so on. It doesn't matter. Ordering does not matter in sets. Okay? I mean, if you're coding Python sets, order doesn't matter. No surprise. They're basing it off of the math definition. On the other hand, for edges, the ordering may or may not matter because of what we're going to talk about in a minute here between like a directed edge and whatnot. But for now, you want to think about these as pairs. So you still got your curly braces, but they're little pairs or tuples per se of data. And what you put in those pairs are the two vertices that the edge is connecting. So the edge itself may not have an identifier, like a name. So you don't see the edges usually called like this is not edge W. Although you could in theory do that, but you don't typically see that. Instead, what we call edge W there would be literally just a pair of A and B. And as you can see here, that's the first one here. So like really tiny, but it's there. So that pair of A to B, that means that there exists an edge between vertices A and vertices B. This is not talking about the direction of this edge because there isn't a direction so far. Again, we'll get to directions in just a minute. I'm just trying to introduce this basic terminology and how you would define these things. So for example, what does C comma D mean right here? Well, that means that there exists an edge between vertices C, well, vertex C and vertex D. I guess let's talk about that English 101 since I do struggle sometimes with that. Vertex is the singular form of the word. Vertices is the plural form of the word, all right? I'm not going to do a spelling test because I struggle with it myself, but you should know it because you can learn it. I'm stuck with sometimes mixing those. As for edges, I guess it's just edge and edge. There's no like edges C. So yeah. Okay. So yeah. All right. So what else I want to say about that? Not really. Obviously, you can see that Y here is not connected to any pair, therefore doesn't show up. So not to any other vertex. So you can see that it doesn't show up here, right? E is connected to two vertices, A and X. There's two edges there. You can see those here, right there and right there. Order between these doesn't matter. Within the pair, the ordering doesn't matter either at this point. So you could write E comma A instead of the A comma E that's there. That's perfectly fine. Because this is what's known as a undirected graph. So what I'm showing you so far is an undirected graph. Another name for that, as I said, a lot of these things have multiple names for the same thing, is what's known as an unordered graph. Mean the same thing for all intents and purposes. So, if this is an undirected graph or an unordered graph, then you should be asking yourself, what is a directed graph then? Is there such a thing? Is it possible to learn this power? It's possible, just not from a Jedi. Well, so far, we got vertices, such as these two vertices, V and W, and we got the lines to define that edge. But there's no arrows. We want to make a directed graph. All you got to do is introduce arrows into the equation here. Now it's directed. Congratulations. So What does that mean though? What does it mean for a graph to be directed like properly? What's the proper definition of that? Well, let me give you. I'm glad that you asked that. You're so inquisitive. This is the definition of an ordered graph, and I'll give you the definition too of an undirected one. So each edge that a graph has must not have arrows, basically. So in formal terms, that's saying each edge, V to W, we're just naming two vertices, V and W, but they don't have to be called that. We're just saying, given that an edge, that is defined as V comma W, where V and W are elements of V, so that means that V and W actually have to exist in graph V. So like this graph right here has A, B, C, D, X, Y, and E. So like they have to exist in that. So given those two vertices exist, this this uh this W, this edge W, or sorry, this vertex W and this vertex V are considered adjacent if and only if, that's what IFF means, V comma W is an element of V. So, a couple of things I want to explain about this. We're using parentheses instead of curly braces. So, right now, before I was using all these curly braces. When you're talking about directed graph, their order matters because you do like a from to sort of scenario. So like in this case, see, the order doesn't matter. You could put VW, you could put WV. It's all good. When you're dealing with a directed graph, you first of all, you indicate that it's a directed edge by putting parentheses instead of curly braces. And now this is like your from and this is your to. So the order matters. So these two edges are technically different. Those two edges are different because the first edge is actually an edge going from V to W, and the second one would actually be an edge going from W to V. So there's a direction involved. So like now it's more like real maps. Some roads are one way, other roads are both directions, right? So if you're trying to represent direction in the map, then you have to use a directed graph. And if your road is one way, then you just put one arrow. If it's two ways, you don't just like not put an arrow because that's not a good thing. It's confusing and you throw people off and they're like, oh, you just forgot the arrow or like bad things are going on. You could do this, acceptable, still very prone to errors. What's more common is just to just draw two complete arrows and just kind of curve them around so you don't get them all confused and mixed up. That's a cleaner way of doing that, okay? Here, I'll throw that in somewhere in here for now. All right, just so that I give you the formal definition for both, let me give you the formal definition of an unordered graph, which should make sense now that you've seen this. Also remember, this little fancy looking symbol is just shorthand for element of. And the IFF is if and only if. Is bidirectional efficient? Well, the more edges you have, the more work you have to do whatever you're trying to do. So it's just a matter of what you need for the problem. If you're dealing with maps, you probably want to have directional graphs. If you're dealing with something that's always bidirectional, such as like social media, because if you're friends with someone, they're friends with you, and it's never the case that it's like a one-sided thing, then undirected is better. So it's more of a find the right tool for the right problem. Find the right tool for the problem kind of thing. Okay, so let's look at the definition and compare them. As you can see, order graph, we use the parentheses. Order matters. V and W is saying V2W. Whereas on the unordered, we use curly braces and the order doesn't matter. So technically speaking, either one of these would be okay. You don't need both, just one of them, and it just indicates there's a connection. Okay? So again, both of these means that V and W must be elements of this graph, or sorry, must be elements of the vertex set, vertices set, vertex set. So like this one here. So they have to be elements of that, meaning that they have to be nodes that actually exist or vertex that actually exist. Okay? And just FYI, we consider W to be adjacent to V if there's an edge. Okay? And that, the same actually for unordered too, you could say the same thing. So like two vertices are considered to be adjacent to each other if there's if there's an edge between them. So if there's a connection between them. So yes, very important. Okay? So I have a very quick example of how you would define this graph. So I'll just draw it from scratch. Suppose I have the following directed graph, which again is also alternative term to directed is ordered. Okay, so ordered, directed, unordered, undirected. So if I say, give me the definition of this graph, like how would you write this graph out? Then you would say, well, the graph itself is made up of all these vertices and edges. And the vertices include A through D. The order of what I list in here does not matter, but I'm just going to do it alphabetical. Why not? I'm getting a call from a UNLV number. Strange. Okay, I don't know. I'm teaching class, so it's after hours too, so it's weird. All right, so yeah, that's going to be your vertices, and now for your edges, because it's a directed graph, you want to use parentheses. Now, the order of the pairs doesn't matter. So the pairs themselves don't matter what order you put them on. You just got to make sure you get the from and to sections right. So what I'm saying is, here I'll make a pull of them and then put them in. So we have three edges, right? We have this edge, which is A going to B. We have this edge, which is C going to B. And the order there matters. And then this one we have D going to C. All right, so we have all three of these. So now let's just dump them in. It doesn't matter what order I put them on. And there we go. This is your full definition of the graph. Graph G. Right here. Okay? It's very important that you understand this stuff because otherwise the algorithms won't make sense. Well, we got 5 minutes, so I'm going to give you one more term for the day, and that term is going to be path. So, what is a path? Well, a path, well, there's a lot of definitions of path, but the one we're interested in about is the one related to graphs, I suppose. And it turns out that a path is a sequence of vertices such that, given all those vertices, you can get from one vertex to another one that you're trying to get to, assuming that it exists, right? So I just, This is nicely written, so I'm putting it there instead of writing it. But so paths are important because, you know, let's say that we want to driving, let's say we want to go from point A to point B, and like we want to know if there's actually the fast. Not only do we want to know if there's a way there, we usually want to know what the fastest way there is, right? So the first step of trying to achieve something like that, and we will learn how to do that once we learn Dijkstra, is we want to find out if there's a way to get there. Like, forget about it being fast. Like, can we actually achieve from this place to that place? For that, we need to find, we have a starting vertex and we have a destination vertex. So let's say we're going from vertex A to vertex F. How do I go from A to F? Well, there may not, if there's an edge from A to F, then I'm done. Like, okay, take that edge, we're good to go. That's like take the highway, we're done. More than likely, though, that's not going to be the case. We're going to have to go through other edges to get there first. So to find out what edges to go is, don't think about looking at the edges, look at the vertices that we got to go to get there. So like, if I got to go from vertex A to vertex B, and then from A, here, let me draw it instead of using hands. I like using hands, but drawing better sometimes. So like, if one way to get from here, which is my A and my F, is to go through this, then sure, that's one way to get there. Of course, the nice one would be there's a straight one, but maybe there's not a direct path. Maybe I gotta go through here. Maybe that's another path that I can take, right? Maybe there's one that goes through here. That's probably nicer, but well, you don't need to add the second line, just that. The point is that the actual set of vertices that you got to take to get to your destination, we call that the path, okay? That's like someone saying, okay, go to the first line and then turn left and then go to the second line and then turn right and then you will be there. That set of instructions, that's what the path is. So it's a sequence of vertices that you need to take to get from one spot to another, okay? That's what this means when it says a path of sequences, the vertices W1, W2, W3, all the way to Wn, such that Wi and Wi plus 1, and all of these are elements of the list of edges available, given the ones that you need to put in here, okay? So that's what a path is. I know there's a lot of fancy terms for this, but I just want to make sure we're on the same page of what a path is, okay? So from there, we will talk about cycles next time, and then talk about the length of paths and talk about how to represent these graphs on a computer. The simplest thing that you can think about is how you've been doing your like ABL trees. You just use pointers, and yeah, you could represent it that way. But there are other ways, such as adjacency list and adjacency matrices. So that's what we'll play with next time. But again, like I said, I'd rather finish telling you all the terminology stuff first, so that if we, when you look at these algorithms and you see the word path, now you know what they're talking about, right? The path to the righteousness or whatever. Okay? So, do we have any questions on that for the last 3 minutes? Now, as for your question about isomorphism, well, hey, you could do it recursively. Just write a recursive function. You know how you did the mirror function in your assignments, what was it, 6 or 7 or whatever? You could use that same concept to check whether a graph is isomorphic or not, and it's actually pretty simple. But it's not efficient at all. In fact, it's probably like not a polynomial algorithm. So it's gonna take a long time to finish. But it's not particularly hard to do from a coding perspective. Just not efficient at all. So yeah. Uh, as for the attendance, well, yeah, that's what I'm saying. NP means non-deterministic polynomial. So it's not polynomial per se. It's exponential or whatever. Basically, it's if we have time, we'll talk about the last day of class between like P versus NP and whatnot. But yeah, so I was gonna defer until next week. But if you would like to start redeeming the extra credit, you can. But what you need to do is you need to send me via Discord or email, and I prefer Discord because it's quicker, but you can do email too. Send me your Twitch account ID not well, whatever the not the ID, but the nickname, whatever it shows up on the chat, and then send me your email at not your email, your name. So Twitch ID, name, and then your class, just because I might get people from 202 as well later on in the day, and uh, and then I'll add the points, and then I'll send you a quick message saying thank you, and then I'll tell you to verify, and then you can verify and make sure you got the points. Okay? So yes, you're welcome to start redeeming them. But yep, okay, that is it for the day. So, I don't know. I just know this is 302. Make sure you put the class though. Again, I care more about the class than the section. Section's either 1001 or 1004, I think. That's not as important. I mean, like, give me the class. Because I need to know which canvas thing to open. Because everything on canvas is combined. So that's not a problem. Just give me the class. Like, say 302, basically. For the next video to come. All right. Well, that's it. So again, I'll upload this later today, so you can check it out replay. But thank you all for watching. And since Wednesday's the test time, you won't see me again until next week. So wishing you all good luck on your exams. I'll be here if you have questions during the exam. And make sure you use your study guide, study worksheet, so that you know what's on the exam and you can practice. And do good on the exam. Make me proud. All right. See you all later.